Thank you so much for that introduction, and I'm glad to know how I got asked to give this talk. I had no idea that I was recommended.
It was recommended, yeah.
Very honored. And I want to thank all of you for your support of this institute. I'm having a wonderful time. I'm here with my family for the month, for the next couple of weeks now. And it's just been great. And we've been even talking about what it would be like to move here. We love the climate.
Sorry about the weather.
You know, it's refreshing. We were living in Seattle for 5 years, so this is much even less than that.
Is your mic on?
They said it was, but
No, it's not. It's. You just have to speak up. That's really for recording.
oh, okay,
Speak up.
okay.
Do you have a tube in here?
So I will go ahead and get started. So I'm going to be talking tonight about how we search for the next habitable planet. And particularly the way that I search for the next planet in the universe where life might exist. We are living in a whole new universe now, where once it was believed that the Earth was the only planet possible to host life. We now know of dozens of planets that have the potential to sustain habitable surface conditions out of the thousands of planets orbiting other stars that we know of. So we are far and away beyond that initial first discovery of the first planetary mass companion orbiting another main sequence star like the Sun. 51 Pegasi b was discovered in 1995. And it was found to be closer to its star than Mercury is to the Sun, with a minimum mass about half that of Jupiter. So not very Earth-like by comparison. Whereas now, a little over 20 years later, we have many, many planets that are in the Earth-sized regime. And an example of that is the TRAPPIST-1 system. So there are 7 planets that have been found orbiting the star TRAPPIST-1, and all of them are Earth-sized or smaller. And so that's kind of puts this comparison in stark relief between those Jupiter-mass planets that we once were only capable of finding to now being in the Earth-sized regime. If we were to look at exoplanet discoveries through the years, we would see that the number of planets found has exploded just in the last several years. And that's largely due to NASA's Kepler mission, which used the transit technique, which finds planets that pass in front of their host stars from our vantage point. And they block out a little bit of the star's light, and that lets us determine the size of these planets. So now Kepler is retired, and its successor, TESS, is going to carry the torch when it comes to the transit technique. Now there's a large difference between Kepler and TESS. Kepler was just staring at one patch of the sky for almost 10 years towards the constellation Cygnus, and just looking for dips in brightness caused by planets passing in front of their stars. TESS is going to be an all-sky transit survey. So it's looking at the whole sky, and it's going to stare and cover 200,000 stars. And if we look at the host star magnitude as a function of planet radius for both the TESS sample and the Kepler sample, we see that TESS is going to cover a very different population, especially in terms of host star magnitude. It's looking at the brightest stars in the solar neighborhood. So these stars are going to be 30 to 100 times brighter than those surveyed by Kepler. And that's really important because it means that these planets found around these stars are going to be easier to follow up on with the next generation of telescope missions. Follow up on to look for signs of life in those planets' atmospheres. So missions like the James Webb Space Telescope, JWST, we hope to be able to use to look for those biosignatures, those signs in the planet's atmosphere or on its surface that only life can make. And James Webb will have an infrared spectrograph on its payload. And so we hope to be able to actually measure the star's light filtered through the planet's atmosphere. And that's going to allow us to hopefully pick out some spectral biosignatures. And it's very good that it's IR because it's at IR wavelengths that the molecules that we're most interested in from a habitability standpoint had the largest number of spectral features. And this is all towards the purpose of finding what I consider the holy grail of exoplanet research. The discovery of another habitable planet like the Earth that's capable of supporting and maintaining life over long time scales, and perhaps currently hosting life. Some of the most interesting planets that we've discovered so far that qualify to be sort of potentially habitable, so they're in that regime where they might have conditions conducive to the presence of life, include Proxima Centaurib B, especially exciting because it orbits the closest star system to us, only 4.3 light years away, which is still pretty far, but it's the closest to us. So, yeah.
Now, you mentioned life. Are you thinking of cellular life?
So when I say life, I mean any kind of life as we currently know it. And that's an important caveat is that we are only looking for life as we know it.
That's what I was wondering. Yeah,
so,
right.
And this is a great question because we don't want to sort of miss the forest for the trees, so to speak, and only be looking for Earth-based life when we could find something completely different.
Sure.
Or miss something completely different. And there are astrobiologists looking for ways that life might carry out its chemical reactions apart from the life that we know of on Earth, and I'll talk more about that. But great question. So Proxima Centauri B is exciting because it's so close. The TRAPPIST-1 system that I already mentioned, all of whose planets are in the Earth-sized regime.
You tell people why we do B, C, D.
Oh, yeah.
It's
just because we want to be
astronomers.
silly. Yeah, the star is usually, it has a name, and sometimes it's just a phone number, a series of numbers. And then the first planet found, the closest planet found is B, and then C, D, E. So there is no A that has classification of a planet. That is the star, but we don't even call the star A. We give it that first name. Yeah. So TRAPPIST-1, yes?
How far away is TRAPPIST-1 system?
So TRAPPIST-1 is about 30 light years away, I believe. So, still in the solar neighborhood, certainly. On par with LHS 1140b, which also is in the solar neighborhood. Now, this planet is particularly interesting because we have both mass and radius information for this planet. And when we have mass and radius, we can understand and calculate a very important property about the planet. What might that be?
Density.
Yes, good. We can get its density. We've been able to calculate that this planet likely has the density that would make it a rocky world. And we know that if the planet has a surface that we can step on, then it's likely that it might potentially have oceans. And so that's why it's we don't often get both mass and radius information for planets, so it's pretty exciting there. So those are just a few of the most interesting that we've discovered so far. Over the next several years, we'll be discovering hundreds more with TESS because of that all-sky survey status.
Do these planets have to have water?
Good question. Yeah, and no, they don't. All life on Earth does.
Yeah.
All life on Earth, from that cell-based life all the way up to elephants, require water. But might there be another solvent that we could use, that life could use? And this is why astrobiologists do have to look for these alternate ways for carrying out metabolic reactions, including other ways to kind of mix up that DNA backbone, potentially. And I'm kind of jumping ahead of myself, but you asked a question, so let's get into it. This idea of we only have, our N is 1, the Earth, and what life needs on Earth. And so we have to just go on what we know life requires on Earth, and there's this diversity of life. So we have some pretty great span of different types of life forms and how they carry out reactions and where they exist on our planet, from those glacial, subglacial lakes to the driest parts of the world. There is always life. To the deep hydrothermal vents, there's life everywhere. So we have to kind of use that as our barometer, what life needs here, but we also have to kind of, in parallel, think about ways that life might be able to exist without those requirements.
So density is important, but is there any way that you're able to determine whether it has a molten core or something like that? That's extremely important to support life.
Yeah, good question. So there are astronomers who are looking at how you could detect the presence of a carbon cycle on a planet remotely from space. Could you, because we don't have any guarantee that exoplanets would have a carbonate-silicate cycle like the Earth, where the silicate weathering rate is adjusted with temperature, right? As temperature goes down, we have less CO2 being drawn down by precipitation, and so less CO2 being drawn down into rocks, so more builds up in the atmosphere. This is a negative feedback that helps regulate our climate. When temperatures go up, more CO2 is drawn down, there's more precipitation, and CO2 gets drawn down out of the atmosphere and cools temperature. So it keeps our planet from getting too extreme in terms of temperature. And so this idea of is there an active interior would be totally tied to plate tectonics. And so there have been thoughts of measuring emissions of carbon dioxide and other emissions that can come from volcanoes remotely from space, or measuring some kind of a sulfur dioxide emission, things like that. But it's still, because of sheer distances and limits in our instrumentation, it's still challenging to be able to tell remotely whether an exoplanet has an active interior. We just kind of assume that it does when we talk about whether the planet is in the habitable zone, which I'm about to explain what that is, but that's a big assumption.
Thank you.
Great question.
So we're not letting you get on with your talk, and we'll probably talk about this in a minute, but it is not at all obvious to me why the size of the planet matters. You could have a planet with much greater density and the life would still survive. So at some point, I'd be interested to know why you focus on Earth-sized objects, but not necessarily now.
No, this is a good question to talk about now. There's been some statistical research that's shown that if a planet has a radius on the order of 1.5 Earth radii or less, then it's probably rocky. Probably. And so that once the planet gets large, like for instance, a formation theory for the planet Jupiter is that planets that had cores of 10 Earth masses or greater then could start accreting large amounts of hydrogen and helium in a gaseous envelope. And so I guess the prevailing thought is that if a planet gets too big, it can accrete a lot of of hydrogen gas and therefore become a gas giant or an ice giant, depending on where it lands beyond the snow line or interior to the snow line. So if the planet is smaller, it's less likely to accrete all that gas and more likely to sort of stay a surface that someone might be able to stand on.
How important do you think the magnetic field is with regard to abilities?
Yeah, that's such a good question. We always think about, when in doubt, say magnetic fields are the reason why we don't understand something. It's such a challenging, people are still trying to understand magnetic fields, but they're so crucial to a planet being able to retain its atmosphere. And so I'm a big proponent of looking for life around these small, cool stars called M-dwarf stars. And M-dwarf planets have a lot of good advantages in terms of their prospects for life on those worlds. But a disadvantage is that because those stars are so small, it's likely that planets, given the low amount of volatiles that might accrete on those worlds, they might not be able to have much water. Magnetic fields might be far weaker on the stars and on the orbiting planets, and therefore they might be less likely to hold on to those atmospheres. And of course, M-dwarfs have all sorts of tumultuous flare activity and harmful radiation that might pelt the surface of a planet. So that's certainly something that's an area of active research. How magnetic field strength varies according to stellar spectral type, and how likely it would be that a planet that you find anywhere in the galaxy would have a strong, robust magnetic field.
Next slide.
So we have all these planets. We're going to find more planets in the coming years, more than we know what to do with, to be honest. And that leads us to a kind of a quality problem. How do we determine which ones to follow up on with this next generation space telescope instrumentation or ground-based instrumentation, given that we won't have infinite telescope time to be able to kind of hone in on that world that might have all the requirements for life? Well, in the past, one might have thought that those of us looking for life would be doing what Jodie Foster did in Contact, listening for ET through headphones. But that's not what I do. In this era, there's a need for a new approach, one that combines both observational data for the planets that we know of with theoretical simulations using computer climate models. And so this combined approach has allowed those of us in this field of exoplanet climatology to gain a better understanding of the likelihood of planets orbiting certain spectral classes of stars to be habitable, and to identify those planets that demonstrate the greatest likelihood of being habitable over the widest range of conditions and factors that are currently unconstrained by observations. So the way that we do this is, first we have to determine, what does it mean to be habitable? What do I mean when I actually say habitable? Habitable for what? Well, when I say habitable, what I mean is a planet that has all of the requirements for life as we know it. So what are those requirements? Well, we know that life on our planet needs a liquid, which here is water, a suitable environment for the formation of complex organic molecules from bioessential elements, sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen, sponge for short, and an energy source, whether it's stellar or chemical. So a terrestrial planet by nature has an energy source, along with the basic building blocks in some form that are needed for life. But what isn't as common is liquid water. And that's because it requires a particular climate capable of sustaining the requisite range of temperatures and pressures needed to keep water in liquid form. So as I just mentioned, life on Earth has a diversity of metabolisms, but they all require liquid water for chemical bonding and as a solvent for chemical reactions. And so that's why liquid water drives our search for life elsewhere. So what determines whether a planet falls within or outside of that required range for liquid water? Well, the primary step has historically been to find a planet that orbits its star at a particular distance where, assuming it has an Earth-like atmosphere, liquid water would be stable on the planet's surface. And so this distance, this range of distances, is referred to as the habitable zone. So what you're seeing is the habitable zone schematic as a function of stellar mass. So we have orbital distance for different stars of different masses. So for the hottest, brightest stars, that habitable zone has to be much farther away from the star, in the same way that you'd have to stand away from a bonfire much farther away than you would if it was just a little campfire. For those cool, dim stars, the habitable zone is much closer in. Too close in to the star, and your planet is in danger of losing its entire water inventory to space in a runaway greenhouse state. Too far away, and the maximum CO2 greenhouse limit is reached. That point beyond which any further increase in CO2 would no longer be sufficient to keep temperatures above the freezing point of liquid water. Now, if only it were this easy, right? Find a planet that orbits the star at a certain distance, and boom, you know that it's habitable. Unfortunately, that's not the case. In fact, there are many factors beyond orbital distance that influence habitability. And if we want an example of that, a prime example, we don't have to look very far. Earth is believed to have experienced a significant climate event while it lay very comfortably in its host star's habitable zone. And this event has been termed Snowball Earth. About 800 and 600 million years ago, the planet, there's evidence to suggest that it was covered in ice from pole to pole. So we need to be able to get an idea of how a range of factors can influence a planet's ability to sustain liquid water on its surface. And so if we start with liquid water, and we think about all the different parameters and factors that can influence its long-term presence on a planet, we come up with the radiative and compositional properties of its host star influence that state, and the planet's individual properties, including its environment. But the picture is actually much richer than I've illustrated here. In fact, when we really got into the nuts and bolts of all the different factors that play a role, it looks more like this. That's exactly what I did when I finally looked at that schematic. I thought, oh! There are a lot of factors that come into play. So over the past several years, myself and colleagues have explored all three general areas of impact. And my focus has been the spectral energy distribution of the host star, the atmosphere and surface of a planet, and the presence of additional companions in a planet system and the orbital configuration changes that can result as a function of that. So the way that I've explored these areas has been through using a hierarchy of different kinds of models, including 1D and 3D models. And so these models are all quite useful for a variety of different applications. And 1D, for instance, radiative transfer models give you a detailed treatment of atmospheric gas absorption throughout the various layers of the atmosphere. Radiative convective climate models they model the vertical energy transfer and convection, and they allow you to determine heat absorption at various atmospheric layers. Energy balance models can be 0D or 1D, usually 1D in latitude, and they are great because you can explore a wide parameter space with very little computational expense. And the most elaborate models, with the most sophisticated treatment of atmospheric circulation and atmosphere-ocean interactions, are 3D general circulation models, or global climate models, GCMs for short. So GCMs have long been used to predict climate and weather patterns on the Earth, and are now being used to predict the effect of anthropogenic carbon dioxide-induced climate change into the 2100s. They've also been used to explore this snowball Earth period of our history, particularly looking at how we exited out of such a state, if in fact we did get into one, given constraints on greenhouse gas concentrations at the time. And one of those theories, which GCMs were used to propose, is that we actually weren't in a snowball state, but actually a mudball state, where there was a lot of continental dust on the surface of that ice, and dust is much darker than ice on our planet. And so that dust, being more absorptive, allowed us to thaw out of the snowball Earth with a much lower concentration of CO2. GCMs were also used to propose a possible scenario for photosynthetic life surviving snowball Earth. If the planet was completely covered in ice, how did photosynthetic life survive? And we have evidence that photosynthetic life existed before and after snowball Earth. And one theory is that we actually weren't completely frozen over, but that there was a narrow swath of open water at the equator, which in certain GCM simulations has been shown to be stable. And this is called the Jormungand state. And this actually led us to think that, if so-called water belt states could exist on our planet, perhaps they could exist on other planets as well. Our planet is only one of 8 other planets in our solar system, not to mention the exoplanets. And so, of course, GCMs were eventually used to look at other planets in our solar system, including Mars, particularly to answer that question of, we know from evidence that liquid water once flowed on Mars, but yet there is no liquid water today. What happened? How could Mars have been warmer in the past for liquid water, given a much fainter sun in the past? How did liquid water flow? And so GCMs have been instrumental in proposing different theories for that. And of course, our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. I love this image. This is the Hubble deep field, ultra deep field, and almost every pinpoint of light here is not a star, it's an entire galaxy. Very long exposure time to get that light from those faraway galaxies.
Back to Mars. If we were looking at that with the instruments that we have now, would we have any idea whether it has a magnetic field or not? If it has a molten core?
Well, let's see. I'm not a Mars expert, but I can tell you based on what we know of, for example, Jupiter's moon Europa, the reason why we know there's a salty subsurface ocean is that that time-varying B field that was discovered by the magnetometer on Galileo, which only a salty ocean could produce. And so I would imagine with Mars being much closer that we'd be able to measure some.
But I'm thinking more in terms of when we're looking out at galaxies
Oh, sure.
away and
Yes.
seeing these planets, we really don't have any sensing of whether or not they have the magnetic field.
That's right. Right. At this point, with those distances, we're not able to measure the presence of a B field on exoplanets yet. But perhaps, I mean, I think that thinking about the molten core and the magnetic dynamo and how there might be sort of indirect methods that are indirect ways to detect something like that remotely that might be used in the future.
Seems to have dramatic effects.
Magnetic fields. Sure. And I mean, this Mars' thin atmosphere certainly is why it cannot host liquid water on its surface today. It would not be stable.
Is that more the absence of a magnetic shield that it can do that, or can't do that? Because it seems to me that it lost its magnetic field some time in the past, and as a result of that, it lost all the atmosphere and the surface water. Would that be something that could lead you astray when looking out at other exoplanets?
If you look at an exoplanet and think that there might be a much thicker atmosphere when in fact it might have lost a magnetic field and then as a result lost its atmosphere, absolutely.
Sure.
Absolutely. And I think this is one of the reasons why people really want to measure the atmospheric composition of the planets themselves to learn whether there would be enough of an atmosphere to be able to sustain liquid water. Measuring atmospheric pressure and things like that, surface pressure. Okay. So of course, it was a natural progression to apply these models to exoplanets, particularly planets orbiting these cool red M-dwarf stars. So how many of you are astronomers in the room? Okay, all right. So this slide I think will be helpful. I didn't want to show you something you already knew if there were a ton of astronomers in the room. Just a quick primer on these are the major classes of stars. Our sun is a G star, a G dwarf star, and dwarf just means these stars are all at the same stage in their evolution where they're all burning hydrogen into helium in their core. It doesn't actually mean that they're small, just that they are undergoing nuclear fusion, hydrogen into helium. M-dwarf stars, because they're so cool and small, they're extremely long-lived. They burn their fuel very slowly. And so they're the tortoises of the stellar family. They burn through their fuel so slowly that their lifetimes are on the order of hundreds of millions and in some cases trillions of years for the lowest mass M-stars. No M-stars have ever died that exist. Their lifetimes are longer than the current age of the universe. And this is, that's right, the fountain of youth exists in M-stars. And this is really good when it comes to thinking about life on planets orbiting these stars, because these lifetimes would offer lengthy timescales for both planetary and biological evolution. It's believed to have taken life on Earth about 500 million to 1 billion years to get a foothold on our planet. So really good long lifetimes for M-stars as opposed to the most massive O-stars. James Dean of the stellar family, right? They live fast, they die young, in a few 100 million years they're gone, right? Not very good for life, given what I just told you about how long it takes life to have evolved on our planet. This is one of the reasons why we're very excited about the prospects for life on M-dwarf planets. Another reason is that they are the most numerous type of stars in the galaxy. This schematic tells you that of all stars, known stars within 10 parsecs of the sun, over 70% of them are M-stars. So M-stars offer the best chance of finding habitable planets through sheer numbers alone. It's also easier to detect planets around M dwarfs with existing techniques, because the transit technique, for example, a similar sized planet blocks out a larger fraction of a smaller star's light, or for the radial velocity technique, exerts a larger RV signal. And that larger transit depth, or that larger radial velocity signal, is easier to measure. We also know from statistics that smaller planets are more prevalent around smaller stars. Bless you. Unfortunately, though, it's not all sunshine and rainbows when it comes to the prospects for life on these planets. So let's go back to the habitable zone diagram. You probably already noticed that the habitable zone is much closer in for these cooler, smaller stars. And in such close-in orbits, you could have some incredible tidal gravitational effects that could ensue. Tidal locking, where a planet's rotation period is slowed down by the gravitational force of the much more massive star. An extreme case of this is synchronous rotation, where the planet's day is equal to its year. And it's always showing the same side to the star. So it's always perpetual daytime on this side, and it's always night on the other side.
Is that true of our moon?
That's right.
Yeah,
Our moon is an example. Mm-hmm.
Let's assume that you find a star or some planet somewhere that you feel that would sustain life. Other than being interesting, what good would it do us?
Well, so this is an important question, and certainly a question we need to be able to answer to get more funding to look for that life. I think my first inclination was just to say, because it's there, we want to know, but that's not going to keep my salary going, right? So I think it's important. This is still a bit more of an emotional response, but to answer that question, are we alone? I think that potentially the human race could find itself much more precious in its own eyes if we were to find out that it's not just us. Of course, there are the material advantages. Perhaps there are resources we could trade or use or things like that, but that wouldn't be my reason for looking elsewhere. I think it's more along the lines of knowing our place, truly our place in the universe, and how diverse life really is and prevalent throughout the universe. But I think that's a question that each person has to answer for themselves in terms of how important or not it would be to answer that question. So synchronous rotation has always been thought of as a bad thing. If you have it always night on this side, super cold on this side, could the atmosphere freeze out on the night side? It could get so cold that that could happen. Because of GCM use and modeling, we now understand that if a planet has a large enough surface pressure, enough of an atmosphere, it could distribute enough heat from the day side to the night side to avoid the atmosphere freezing out. Also, because of climate modeling, we understand that there might actually be a benefit to a planet that's synchronously rotating around its star. If the planet has an ocean, it could build up a significant cloud layer on the day side. Clouds are very bright, and they could reflect a lot of that incident stellar radiation back away from the planet, buffering it against a runaway greenhouse and allowing that planet to orbit much closer into its star than it would otherwise. So synchronous rotation is no longer this sort of like end-all in terms of habitability. Of course, all of the intense UV radiation is an issue because these stars are so long-lived. They have these extended, we call them pre-main sequence phases. On the main sequence, a star is doing that hydrogen to helium fusion. Before it gets onto that track, it can be very tumultuous, and there can be a lot of radiation exuded from the star. It might be that life would have to exist at the bottom of an ocean to escape that X-UV radiation. Work has shown that these pre-main sequence phases could last as long as 1 billion years. Right? That's on the order of the time scale for life to evolve on a planet. And the oceans could be evaporated up into the atmosphere, and that lighter hydrogen escapes. The water is broken up, photolyzed by sunlight, starlight. The lighter hydrogen escapes. The oxygen remains behind and could present a false positive. You might we might measure O2-rich planets with telescope instrumentation and think, oh, there's oxygen there, there's life, when in fact these planets could be long desiccated. So I wanted to give a balanced view when it comes to habitability. There are some, for M-dwarf planets, there are a lot of pros, but there also are some concerns. And for more information on all the pros and cons, we've written a review paper that covers comprehensively all that we know about M-dwarf planet habitability, both observationally and theoretically, over the last decade. What has really excited me is thinking about how a star's light interacting with a planet's atmosphere and surface can influence a planet's climate and habitability. So when I was a grad student, you know how you're always thinking about, what should I do my PhD on? I want to know, like, that light bulb moment. What's the thing? Nothing. No. Know what just happened. So a classmate presented this paper in Journal Club, and it was a suppositional paper. There was no modeling done, but it was just using simple scaling arguments to show that ice-albedo has this wavelength dependence, and therefore ice could behave differently on planets around different types of stars, which emit at in different portions of the spectrum and different percentages across the EM spectrum.
What's albedo?
Oh, excuse me, thank you. Albedo is reflectivity, how reflective a surface is. It's usually, it's on a scale of 0 to 1, so if a surface has an albedo of 1, it reflects everything that it gets from its star. If it's albedo of 0, it's very absorbing, it absorbs everything. So that was my bingo moment. That's what I wanted to do. And I emailed Manoj Joshi, the first author on the paper, and said, are you going to do any more work in this area? And if so, can I be involved? He said he wasn't, that I could take it and run with it, but he wanted to be on any papers that I wrote as a consequence. So we co-authored a couple of papers together on this whole concept of ice-albedo feedback and how it and the climatic impact of it on planets orbiting different types of stars. And so on our planet, we think of ice as being very bright. And the more light that ice reflects, the less it absorbs, the colder the planet gets, reflects more light, temperatures get colder, etc. It's a positive feedback process.
What's the Earth's albedo?
Including atmosphere, about 0.3. But ice albedo has this wavelength dependence. And so ice absorbs longer, redder wavelength of light and reflects shorter, bluer light. An example of this is looking at this iceberg. This iceberg looks blue because the redder light from the sun is absorbed on its way through the ice. Only the blue light makes it all the way to the bottom, and then it reflects back up to our eyes and we see blue ice. I'm showing you two end members on our planet in terms of ice grain size. So here, this beautiful blue ice looks blue because there's not that many grains. It's very coarse grained, and so there's nothing to really scatter the light. So that whole process of the red light being absorbed and only the blue light, getting to the bottom and reflecting back, we can see that much more easily on this type of ice, blue marine ice. Whereas the finest grained ice is snow. And it's very fine grained, so lots of surfaces to scatter light, and so we see this bright white color. So let's look at this effect more quantitatively with a plot from one of my papers. So here's albedo, that reflectivity as a function of wavelength for ice of these different grain sizes. So snow is at the top, that's there, that end member. Blue marine ice is down here, and we've modeled intermediate spectra between those two end members, and we show an ocean spectrum and an average land spectrum for reference. Ice on a planet orbiting a star like the sun is going to reflect most of the light that hits it, because ice reflects strongly where the sun emits strongly, in the visible and the near UV. But ice orbiting a cooler, redder M-dwarf star is going to absorb much of the light that hits it, because ice absorbs strongly where M-dwarfs emit. And so we carried out a comprehensive exploration of this phenomenon using a hierarchy of computer models. And I'll share with you some results from using the GCM, those 3D climate models. Yeah?
Before you leave the small grain, different grain sizes, how does that differ from old ice and new ice?
Yeah, that's a good question. Well, it just depends on Usually fresh ice, or fresh, depends on the grain size. So I don't know what grain size you're talking about, but if it's...
In Earth observation, I know they differentiate old ice and new ice, and I've never understood. Is that a grain size issue, or what is it that differentiates?
Yeah, because it is grain size dependent, but I think largely fresh ice tends to be higher, more reflective, and because there's fewer particulates that end up becoming a part of that as time goes on.
So it may be a cleanliness issue.
I think that's related, certainly. So yeah, it's a good question. There are many different forms that ice can take over its lifetime, so to speak. So what we did in our GCM is we put 3 different planets at equivalent stellar flux distances. So they started off at the distance from their star where they got 100% of the modern solar constant. So they got an Earth-like amount of incoming stellar radiation, or installation, as I'll call it. And then we dialed down the installation and observed at what point these planets went into a snowball state. And so on the y-axis, you see the mean ice line latitude. So if the ice goes all the way to 0, that means the planet is totally ice covered. It's a snowball. If the latitude is at 90 degrees, there's no ice on the planet. And this is planets orbiting an M dwarf star, a G dwarf in black, and an F dwarf. So F dwarf is a little bit brighter than the sun. And what we saw is that the F dwarf planet, which emits a lot of radiation in the visible and near UV, even more than the G dwarf, became a snowball with just a 2% reduction in installation compared to modern Earth installation. The G dwarf became a snowball with an 8% reduction, and the M dwarf didn't freeze over until its installation had been reduced by 27%. So the slope of these lines is a measure of the climate sensitivity of these planets to changes in stellar insolation. And this shallower slope for the M dwarf planet tells us that it appeared to be less susceptible to a snowball state, whereas the F dwarf was more susceptible. So to see why that's occurring, let's look more deeply into 2 planets that exhibit similar climates but receive vastly different distributions of spectral energy. So the G dwarf at 100% of the modern solar constant, so similar climate to modern-day Earth, has the same ice line latitude, and it turns out same global mean surface temperature as the M dwarf, receiving 90%, 10% less installation. So we'll look at those 2 planets. What I'm showing you here is the difference in temperature throughout the atmosphere between those 2 planets. So what I did was I subtracted the G dwarf planet's atmospheric temperature profile from the M dwarf planet's temperature profile. And pressure now is on the y-axis as a function of latitude on the planet, and you're seeing difference in temperature. And what we see is that there's a lot more heating, so higher temperatures happening throughout most of the atmospheric column in the tropics and at the poles. Right? The difference in temperature is above 0. And what the reason for that is there's CO2 and water vapor in these planets' atmospheres. These are Earth-like atmospheres. CO2 and water vapor absorb strongly in the near infrared. They have absorption bands in the near IR. But the M dwarf emits a lot more in the near IR than the G dwarf. So there's a lot more, and we call this shortwave heating. So climate scientists have this strange thing where they say shortwave, and what they mean is incoming stellar radiation, which is strange because astronomers think of shortwave and we think shorter wavelength. But climate scientists mean everything that comes down from the star. So there's a lot more shortwave heating of that incoming stellar radiation happening because of that CO2 and water vapor absorbing the near IR. So the atmosphere is certainly playing a role. What happens with this shortwave heating happening is that ends up reducing shortwave that actually reaches the surface that's needed to drive convection. And the result is that you have less cloudiness at most heights, less precipitation, and more shortwave absorbed by the planet. So it makes these planets much more stable against convection. And so that's certainly playing a role, the atmosphere. And then, of course, what's happening at the surface. If we look at surface albedo, so how reflective the surface is, for that G dwarf versus the M dwarf, we see that where there's ice on these planet surfaces, similar to modern-day Earth and the high latitudes and at the poles, that ice has a much higher albedo on the G-dwarf planet and a much lower albedo on the M-dwarf planet. So that allows the M-dwarf planet to absorb more radiation. And you end up having similar overall temperatures, but that lower installation that the M-dwarf planet receives, it compensates for it by absorbing more radiation and more shortwave throughout its atmosphere and on its surface, so that its poles are warmer, and you end up getting a similar climate to a planet that receives 10% more light from its star.
I just have to ask. We like to fly at 35,000 feet because we're above the troposphere and the convection zone. Do these models have an equivalent size of the convective layer in the bottom?
Yeah, a lot of them just go to the troposphere, but most of them go all the way up to the stratosphere.
So when you say there's less convection, do you not have a troposphere on the end?
Yeah, we do. Yes, this is throughout most of the troposphere. Yeah, so this is most of the free troposphere that we're seeing this.
Okay.
So you're saying less convection is better?
So what it ends up happening is when you have a planet that's more stable against convection, then you end up actually holding a lot more heat at the surface than you would if you were experiencing a lot more convection. And I'll talk a bit more about what's happening with the Hadley circulation regarding that too.
Doesn't that balance out the heat in the planet? The convection, isn't that responsible?
Yeah, usually that convection with, through Hadley circulation, et cetera, can carry energy from warmer regions to cooler regions. But if you have a planet that kind of can hold a lot more heat at the equator, then you can have a warmer planet overall. So, and we're going into this too. So if a planet, so we talked about how the M-dwarf planet seems to be harder to freeze. What if the planets were in snowball states, like they were so far from their star that they'd become ice covered, and they only had the steady brightening of their host stars over time to depend on, to thaw out? How would stellar spectrum influence that process? So we ran similar simulations, but this time we started our planets in so-called cold start scenarios. So first we were starting our planets, remember, at the warm starts, the distance where they got Earth's amount of radiation. Now we're starting them in snowball states, and that's what you see as the blue asterisks. So the red circles are the original simulations I just showed you. That's the warm start. The blue asterisks are cold start. And we dialed up the installation and observed at what point the planets thawed out of global ice cover. What we found was that not only does the M-dwarf planet is harder to freeze, it's also easier to thaw out of a snowball state. And once it does thaw, it thaws with a much shorter jump in ice line latitude. Whereas the hotter and brighter the star, so this is the M-dwarf, G-dwarf, and F-dwarf planet. The hotter and brighter the star, the higher the jump in ice line latitude. The F-dwarf planet exhibits almost binary behavior, where it's either completely ice covered or virtually ice free. So here's a question for you. Which of these is better for life? Maybe the M-dwarf. Maybe the F-dwarf, because it's got that extreme ice line jump. We could probably debate that all day, but what does seem clear is that the M-dwarf planet has a more stable climate. It's harder to freeze, it's easier to thaw. And the reason for that is certainly the ice playing a role, the ice-albedo, which I just talked about, but also Hadley circulation, which is on our planet responsible for the net transport of heat to colder hemispheres from warmer or colder regions from warmer regions. I'm showing you here a cartoon which shows sort of the annual mean Hadley cell. If I were going to show you an actual plot, it would show you the one dominant Hadley cell responsible for the net transport of heat to the colder hemisphere. So that's what I'll show you in the next slide. But we're transporting heat from, usually on our planet, it's the equator, to higher latitudes where it's colder. So here is that seasonal plot. And so we've got planets that are about to deglaciate. They were totally ice covered, and then they're deglaciating. And this is northern hemisphere wintertime. On the left is now the F-dwarf. Middle is the G-dwarf planet, and then the M-dwarf on the right, just prior to ocean opening up in the equator. And we have this dominant Hadley cell it's much weaker on the M dwarf, and I'm showing you quantitative numbers. This is also called a meridional stream function. You can think of it as a mass overturn, a mass flux. And so you have a much weaker Hadley cell on the M dwarf planet, and it's squatter and it's weaker. And that is due to that increased shortwave heating happening throughout most of the troposphere, right? Which is reducing shortwave reaching the surface that's needed to drive that convection. And so what you end up happening is more heat is retained in the tropics. And so that allows you to thaw more easily out of global ice cover. So these plots where you sort of show the warm start and then the cold start and you kind of link them together are often called hysteresis plots. Hysteresis is the lag in physical response. Once you reverse some kind of a change that you've implemented, and you see at what point the response changes back. And we see this sort of smaller hysteresis on the M dwarf planets. We've been doing this with other climate states. We see this throughout the climate states, from snowball through water belt to temperate to even moist greenhouse, which is just before you have a runaway greenhouse, you have a moist greenhouse state. And we've seen that the redder your star, the smaller your hysteresis, and the more effective your solar deglaciating ends up happening. And that's due to that albedo of ice, as well as the atmosphere contributing. So I just wanted to highlight some of my later work looking at a new surface type besides just salt-free ice. Is something called hydrohalite, sodium chloride dihydrate, NaCl2H2O. And this can precipitate in bare sea ice at low temperatures. So these are brine pockets, and you have liquid here in the brine pocket on the left, and then this picture was taken 15 minutes after. It's 15 minutes apart, and they're both taken at about minus 28 C. And you see that the liquid has now precipitated as hydrohalite, and it's blocking out the light. And what you can end up have happening is hydrohalite can form at low enough temperatures in sea ice, and its albedo spectrum is very different from salt-free water ice. It actually is very reflective in the near IR, whereas snow and ice become very absorptive. And so this was important to quantify this effect for M dwarf planets, given this is the region where they emit strongly. And so we carried out more GCM modeling, where we looked at what if we were to incorporate an albedo parameterization for hydrohalite formation, and we ran simulations with that albedo parameterization and without it in a control case, and observed the difference in temperature between simulations as a function of latitude. And we saw that, so these are for M dwarf planets at different installation levels and G dwarf planets. And we see that for M dwarf planets at ranges of where they get installation that would put them in the habitable zone, we start to see a difference. So we can actually form, it gets cold enough on even habitable zone M dwarf planets for this surface type to form. And synchronously rotating M dwarf planets are even more susceptible. So they're susceptible at 90% installation, because on the day side, the temperatures get, the minimum day side temperatures are colder than if a planet is rapidly rotating. So I think I'm at my time, or probably, or pretty close to it, but just to give you a flavor. What? Yes?
2 more minutes. Yeah.
Okay, 4 more minutes. We can do these GCM simulations for general parameter studies, like how does a particular factor influence a type of planet. But we can also apply them to actual observed systems. And an example of this that happened pretty early on was looking at a planet called Gliese 581G, where Ray Pierre Humbert, who's sort of the grandfather of the field of exoplanet climatology, or I consider him the grandfather, determined that there could be a scenario called eyeball Earth, where your planet is frozen over everywhere except for right at the substellar point, and there's this little eyeball of open ocean, and that could actually be stable. And that led us to think about how that could be applied to other planets. And he actually sent me the other day, he did this on Google Earth, where this is the eyeball state. that you could actually have that form. So I've actually applied GCMs to multiple planet systems, because that is where, I mean, our solar system is a multiple planet system, and we could actually look for the next habitable planet. It's more likely that that's going to be residing in a system like that, where it's not alone, these planets. Kepler-62, which is a 5-planet system orbiting a K-dwarf star, so a little cooler than the Sun, but not as cool as an M-dwarf. The outer 2 planets are in the habitable zone and are the most interesting, but 62e receives 20% more insolation from its star than Earth gets from the Sun, so it's probably too hot with an atmosphere to be habitable. But 62f was more interesting because it gets 40% of what Earth gets from the Sun. So we definitely would need to have some sort of greenhouse gas concentration, but it was the best prospect for habitability in the system. So I actually did more than just GCM simulations. I started with N-body simulations, which are these simulations where you can, N number of bodies you can choose to evolve their orbits over millions of years and see how the orbits change, how their obliquities, how their eccentricities, etc., how their orbital distances change. You can give your sun a certain mass, your planet certain masses and certain other values, and then see how the system evolves with time. And so these were the results from those N-body simulations. I wanted to identify the range of eccentricities, so how oval-shaped the orbit is, that would still allow the system to be stable. The range of eccentricities that Kepler-62f could have. And so we have fraction of stable configurations on the y-axis as a function of the eccentricity that I gave the planets to start. And we found a very sharp range that there was, after 0.32, the fraction precipitously dropped. And so this was our range, that 62f could have an eccentricity between 0 and 0.32. We don't know the eccentricity of this planet. So this allowed us to put some constraints on what was possible for the system to be stable over a long period of time. And we used these N-body constraints to inform our GCM simulations. And this was the first time that had been done.
Excuse me, what's the eccentricity?
Oh, 0.0167, very low. Yeah, almost circular. And most of our solar system planets are pretty much circular, except for Pluto, and that's one of the reasons why it's demoted. So then we ran GCM simulations with that eccentricity range to inform us. And we found that if you use the lower limit of that range, 0, so circular orbit, the planet, 62f, could have an open water in the tropics, similar to modern-day Earth. It would have to have 5 bar of CO2, so a lot of CO2. But that is plausible where this planet is, assuming it has an active carbon cycle. This is within the maximum CO2 greenhouse limit, that edge, that outer edge I talked to you about. Earth-like obliquity. So that was important. But what if the planet doesn't have an active CO2 cycle? There's no guarantee that exoplanets do. So we wanted to see if there was any way this planet could exhibit above freezing surface temperatures sometime during its year if all it had was an Earth-like amount of CO2. So one of the ways that we explored that was changing obliquity. So obliquity is interesting because it's been long established that when you have an obliquity of 54 degrees or greater...
What's obliquity?
Obliquity is the tilt of the planet's axis. So our planet has an obliquity of about 23.5 degrees, as opposed to being straight up and down. And it's why we have seasons. So this is Earth's obliquity. So our installation, the pattern of our Earth's radiation across latitude looks like this. A lot more radiation we get at the equator than at the poles, right? So that explains our temperature differences. But if you have an obliquity above 54 degrees, it flips, and your poles get more installation, more incoming stellar radiation than your equator. And so we explored obliquity by assuming a very high obliquity, 60 degrees, for Kepler-62f. And then we compared it with an Earth-like obliquity, and we found that at that high obliquity, we got above freezing surface temperatures during southern hemisphere summer. Not the whole planet's year, but during this particular time. And the reason for that is that we assumed a very specific orbital configuration. We assumed, like Earth, that the angle of the vernal equinox, where you have equal day and equal night, with respect to the planet's closest approach to its star, was 90 degrees. Earth's is about 102. And what that does is it means that southern hemisphere summer coincides with the planet's closest approach to its star. So you have southern hemisphere summer, you have closest approach to the star, and that can maximize the effects of high eccentricity, high obliquity, and might actually melt ice sheets that you form during colder seasons. Say you're farther away from the star, and you form ice sheets. Maybe you melt them when the planet's close to its star. So we're playing around with different ways that the planet could experience above freezing temperatures.
Is there any information or current measurements at these distant planets that tells us anything about their obliquity, or can we just...
People are working on that. Actually, there's a scientist here, Rebecca Dawson, who's here for this program, the Better Stars, Better Planets program, that has given a talk today about constraining eccentricities for larger planets using transits. So it's definitely an observational issue, but we are trying to be able to constrain those orbital parameters for exoplanets. And it's, of course, much easier to do when your target is bigger. Finally, we had to entertain the possibility that Kepler-62f could be synchronously rotating. And we performed tidal simulations that showed us that it could be, that there are certain scenarios under which synchronization, spin synchronization, has been attained. And so we were able to put constraints on how much CO2 would be needed in a synchronously rotating state to both have a large enough swath of open water at the substellar point to remain stable, and to distribute enough heat from the day side to the night side to avoid this atmosphere freezing out issue. So all of this work is taking us, hopefully, closer and closer to moving from artistic concepts of exoplanets to hopefully one day having an actual picture, like this Ansel Adams photo taken of the Tetons in Snake River in 1942. If nothing else, please take away this main point, which is it is through combining both observations and theory that we're going to be able to come up with the most accurate assessments of planetary habitability for these newly discovered systems. I just want to make sure that I plug my organization. I have an organization called Rising Star Girls, which teaches astronomy and astrobiology to middle school girls of color using theater and writing and visual art. This is how I combine my two backgrounds. And it's also how we get these girls to have a deeper connection to what they're learning, because the creative arts are inherently artistic and personal. And so it allows them to be able to have an ownership of the star or galaxy they're learning about. And the hope is that once the intense math comes in as they get older, they'll be less likely to abandon these fields because they have actually written a poem or drawn a picture or studied something that is personal to them.
How big are you?
How big
is the group? How...
So it's been a one-woman show when I was a postdoc, and now I did get an NSF career grant last year, so we're going to be taking it on a global platform. So we're hoping to carry out Zoom webinars so that any girl in the world with an internet connection can actually participate. But we are looking for groups of girls to kind of beta test that Zoom platform. And we'd love to be able to take it, to be able to actually travel to different parts of the world and physically do these workshops.
Schools? Different schools?
We can do them at schools, YWCA's after-school programs, Sci Club for Girls in Boston. We've done some programs there. And so, yes, we can always use more donations in that area of bringing the mission. But the whole thing is that we want the girls to understand that just like if we were to look at the Milky Way in one type of light instead of different types of light, we'd miss out on so much if we just looked at one range of the spectrum. So too, there's so much to these girls than meets the eye. In middle school is when girls start to become quiet, they raise their hands less often, they become more concerned about with how they look and less concerned with how they think and feel about the world. And so we want them to understand that who they are and what they think and feel is important. So they actually design their own constellations and write their own constellation myths and design their own exoplanets and make choices about what the planet has in terms of life or no life and why. And so for more information, please visit our website and learn more about what we're planning to do in the coming years. And I want to thank my host institution, KITP, for the opportunity to be here and to give this talk, my funding sources, and my collaborators. And thank you all for your attention.
Go back one slide so they can get that website on. I'm confident there are a few more questions.
I have a quick one. Have you looked at any planets in the binary systems?
I haven't, but people are and have. I think there's a paper, I'm going to get his name wrong, but Nadir Hagigapur has looked at how could you actually combine the flux from both stars and determine how, like, what does the planet actually see? How does the radiation change with that binary system? And so people are actually creating equations to determine how that incident radiation would change depending on the binary system orbit and all that. But I think that's actually something that has or will be a topic later on in the conference week that we have next week too. Yeah.
Thank you.
One of your earliest slides showed several planets with exoplanets and it listed their orbital periods, and they seem to be extremely short. Why is that?
Yeah, so these planets that are in the habitable zone of these cool small stars have to be much closer in, and so the time it takes for them to go around is much shorter. So the orbital period for habitable zone M dwarf is something like anywhere from maybe 15 to like 45 days, as opposed to for our planet, right, 365 for a G dwarf.
You should say a little bit about why that makes it easier for TESS.
Yeah, so that's great because when you find a planet, we find this sort of dip in the light that we think is because a planet is crossed in front of a star. We have to confirm that, and usually it takes at least a couple of transits to confirm. If you're waiting for a planet around a G dwarf to transit, you're going to have to wait 2 years, 2 of our years, to confirm that. Whereas an M dwarf, you have to wait much less time, right? So maybe a couple months to confirm. So that's another reason why we're wanting to kind of go after M dwarf habitable zone planets.
Astronomers are not patient.
How inaccurate can your data end up if the transverse of the planet isn't directly between you and your eye? If it's a little bleak, if it's kind of coming across the poles, you might think, well, it only zipped to the, so you might think it's faster or farther away, or
and there's huge observational bias. That's such an important point, because the planet could be transiting its star, but from our vantage point, the planet is going around its star like this. Sure. So from our vantage point, we don't see a transit. We only see a transit if it's going around like this, assuming that you guys are the telescope. If it goes like this, or like this, or like this, but there's at some point you won't measure the transit. And so I think the statistic, they are correcting for the observational bias. When we talk about how many planets actually exist, we are trying to correct for that. But it certainly means that we could miss finding that planet because it might be one of those in this configuration from our vantage point.
Or even if you do see the transit, it's not at the equator, it's maybe closer to the pole at which you observe it. So
sure.
the period at which it's that dip might lead you to an incorrect conclusion.
That's absolutely true. And transit timing variations are another thing too, which the transit, we measure a transit and that tells us the period of the planet. So we think, okay, we should see that transit at a certain time than the next. But if there's a difference, a delay, that could mean another planet is in the system that we didn't measure, that's tugging on the planet, that's changing that transit time. And so that's, in essence, the principle of transit timing variations. It's how we can discover other planets in a system. But it also is in degeneracy too.
Last question.
So is gravitational wobble still a valid method?
Absolutely.
As well as direct observation with better and better telescopes.
RV, radial velocity, also called the Doppler wobble technique, is, before we had Kepler, was the prevailing way that we found planets. And it's still used.
The old method.
That's right. But it's still being used because it is important, and many of the Ground-based telescopes are using it on the ground. So it's the combination. And I think that actually one of my colleagues at UCI, Paul Robertson, has been developing instrumentation that's really pushing down the precision of RV to be able to look at, I think he said, it's like arc second. It's very, very good precision. Or maybe it's like 10 centimeters per second. It's something very, very small to be able to hopefully detect an Earth from the ground. So yes, RV is still in the game for sure.
Can you explain it? Because I'm not sure I understand what the
Doppler. So yeah, and I'm not an observer, so, but and I actually had you told me to take it out. So the technique is. When a planet goes around a star, the planet has there's a wobble that the star experiences because the planet is pulling on the star, but the star is also pulling on the planet. So they're actually not. The planet is not just wobbling around the star; they're both wobbling around something. And what is that thing? The common center of mass between them. That wobble is just much smaller for the more massive star. And so that amount of wobble we usually measure in some amount per second. Meters per second has been historically as small as we can get down to. But now we're starting to be able to get down to centimeter per second precision, which is on the order of an Earth around either the sun or a red dwarf, or I'm not exactly sure what that equates.
It's a fast snail 20 light years away. Thank you.